Good morning. Welcome to FSI312, Replatforming for Reinvention, Modernizing Mainframes at Goldman Sachs. So today, customers have many business reasons for migrating and modernizing their mainframes to the cloud. And we also recognize that they are complex to execute, and there's whole sets of challenges and risks associated with them. So the good news, fortunately, based on our experience at AWS, we have learned from successful mainframe migrations projects and came up with identifying design practices, best design patterns, best practices, and lessons learned that you can leverage for your own future mainframe migrations. Now, although there's not a single design pattern or a single one-set-fits-all for mainframe modernization, there is one pattern that consistently provides benefits to our customers, and that's replatforming. And the reason being is that it has value both in the short term and the long term. In the short term, it accelerates your mainframe migration to the cloud, and in the long term, because you're already in the cloud, you can get more modernization, future modernization, with that workload being in the cloud in the first place. So today, that's the topic we're going to be talking about this morning. And what better way to do that is with a real project and a real use case by the talented team at Goldman Sachs. And they're going to be taking you through their end-to-end journey for mainframe modernization and migration. And by the end of the session, you're going to learn how they were able to expedite the speed of their project. They were able to increase scalability and capacity. And they were also did this without compromising their commitments to the business and to their customers. My name is Sherry Moran. I'm a Principal Solutions Architect for AWS, dedicated to the Goldman account. And I'm going to take you through a quick overview of the agenda, and then we're going to meet the Goldman Sachs team. Okay, so starting off, we're going to talk a little bit about the GS Asset business and its evolution over time. And then we're going to talk about InvestOne, which is really the focus of this presentation. It's their business-critical mainframe workload. They'll talk about the challenges that they had and the reasons why they decided to migrate and modernize. And then we'll get more technical in terms of the legacy design, what it looked like, components and dependencies. And then we'll contrast that with the reinvented design on the AWS cloud in terms of services and design patterns. And then we'll wrap it up with a discussion on SDLC development for COBOL, the unique way that Goldman is handling that in this new environment. And then we're going to wrap it up with lessons learned. So without further ado, it's my pleasure and privilege to introduce the Goldman team. Victor Balta, Managing Director of Goldman Sachs, is going to be starting up with the business case. And then the tech case is going to be covered by Yitz Lorner, Technology Fellow for Goldman Sachs. With that.
Great. Thank you, Sherry. So first off, welcome to everyone, and thank you for taking the time to come here and hear us speak. My name is Victor Balta, and I've had the privilege for being at Goldman Sachs for the last 10 years. Prior to joining Goldman, I spent time in Citi's capital markets engineering team, and I started my career building solutions for hedge funds. I currently am the co-head of portfolio servicing engineering in the asset management division within Goldman Sachs. Our division oversees more than $2 trillion in assets under supervision. This makes us a top 10 asset manager, and we pride ourselves on being a global leader in active asset management. So when you talk about asset management, we basically have two sides of the house, the public side and the alternative side. When you're talking about the public side of it, we're really talking about our public funds, which cover more standard products like fixed income, money markets, ETFs, et cetera. And the clients that come to us are institutional investors, pension funds, and they're coming to our funds to satisfy their investing strategies. On the other hand, we have the alternative side. So these alternative strategies are across both private markets and liquid alternative strategies. And here, these are our clients coming to us to drive growth, diversify their portfolios, and generate income. And when you look at some of the products we have here, it ranges from anywhere from private credit and equity to all the way to life sciences and real estate, and almost anything in between here. So those are the two sides of the house. Now, where do we sit as an engineering organization within the broader asset management division? We are part of a larger group called the Client and Portfolio Servicing Engineering. And this area supports both the public and the alternative side of the business. And now there are three main groups within this. The first one is our investment and portfolio servicing group. Now think about this as everything post-trade execution, so confirmations, settlements, portfolio accounting, reconciliation, et cetera. We have client servicing, which is how we engage with our external clients. So think about account opening, billing, reporting. And then finally, we have data platform and services. This is how we're going to be distributing data and the consumption of data for both like product data, benchmarks, et cetera, in that stage. For today's session, though, we're really going to focus on portfolio accounting and specifically the IBOR, which is the investment book of record. So when we talk about portfolio accounting in the asset management division, we're really talking about two main components. The first one is a vendor software called InvestOne by FIS. And this software provides us the account functionality to create an investment book of record, to create both a net asset value and a general ledger view. And the second component within there is Goldman's own homegrown Cobalt orchestration layer. Now, our orchestration layer and InvestOne both run on mainframe, but our orchestration layer basically encapsulates InvestOne and makes it work for Goldman Sachs Asset Management's unique problems and use cases. So some quick facts on this area. We first got engaged with FIS, and that wasn't FIS back then, but InvestOne back in 1991, and for the last 30 years, we've been actively developing and enhancing this platform. Currently, we have a team of over 20 global engineers supporting the platform. And when you talk about our compute or our resourcing, about 60% goes towards InvestOne, while the remaining 40 are on Goldman's proprietary Cobalt orchestration layer. So here's a quick list of all the functionality we cover. So shadow books, portfolio accounting, transaction processing, calculations, everything from overnight. But I want to just take a quick minute to highlight shadow books and why this is important for our business. So as an asset manager, we're on the buy side of the business, which means we're not the custodian of any of our trades. We actually interact with 40 plus custodians on the street. So what a shadow book basically does for us is it allows us to create a holistic view of our positions and transactions. And even more than that, corporate actions, asset servicing events, subscription redemptions. And the reason why this is so critical for us is because for our portfolio managers and traders to be able to trade on the following day, we need a golden source of data. And that's what we're doing here. This next slide is a very high-level macro view of the existing architecture, with InvestOne being the green box in the middle. And what we're trying to highlight here is a few things. North of InvestOne, we have all the consumption of all the producers of the data. So think trades, subscription redemptions, any type of asset servicing event, security transfers, et cetera. Those are all feeding into our portfolio accounting platform. Downstream of there, we're going to have the distribution of data. So this is going to be going to compliance, regulatory, portfolio managers. And then on the right-hand side, leans to that shadow book functionality that we have to provide. We have many different external parties, not just custodians. It could be broker, fund administrators, electronic confirmation platforms. We need to integrate with all of them and pull that in to create our nightly shadow book. So some business challenges. So we've been at this for 30 years, but we had many business challenges throughout the time. So first and foremost, we have a vendor. They're migrating everyone off of mainframe into their new platform. So we have a vendor pushing us towards that. A very high cost. Compared to a traditional platform on a more modern architecture, it's very expensive to run on mainframe. Complexity and integration. You don't have the same number of APIs or data contracts that you could integrate with the mainframe. We're very limited on what we could do. And then lastly, sourcing. So sourcing high-skilled Cobalt engineers with that financial background is becoming harder in the modern day. But what's probably our biggest issue and why we're here today is the fact that our inability to scale horizontally anymore, which is our biggest business problem we have today. So why now? Like I mentioned, we have a challenge from the business that they want to continue to grow our business. There's certain areas like SMA direct indexing that have significantly grown our number of accounts, which balloons the number of transactions and tax loss that we have to deal with on a nightly basis. So we have a critical deliverable to the business to provide the capacity to support them. And we know that we have a longer view, 5+ year view on modernizing the whole platform, but the business couldn't wait those 5 years or however long it's going to take to get there. So we had multiple options when we got into this. The first one was to rewrite the COBOL orchestration layer, the homegrown Goldman COBOL code. And the reason we didn't do this was twofold. First, we don't know where the target state is, and we didn't want to start rewriting something if we don't know where our target state is going to be eventually. And second, we have 30 years of customization there, so that would be an unrealistic undertaking to rewrite that or to refactor that. Next, we looked at optimizing our Cobalt layer or our mainframe code. Now, this is actually something we've been doing for the past 30 years, and the fact that we've been able to keep pace with the business for the past 20+ years is a testament to the hard work the team has done and the ingenuity they've done there. But we basically hit a ceiling because our current implementation runs on a single CI/CS or CICS region, and we have a limitation on how much MIPS or compute and memory we can allocate. We would have to shift to a multi-CICS region implementation, which would be a major refactoring of everything. So that was not realistic. Then we looked about moving off of the vendor's mainframe to non-mainframe version of the code. But the problem there, again, is that 40% is our own code. So we couldn't go half and half. That wasn't going to work. And where we ended up landing is like, let's take a pragmatic approach, run this on an emulator, and lift and shift from mainframe to AWS. So on that note, I'm going to hand it over to my colleague Yitz, who's going to walk you through our implementation.
Thank you. Thank you, Victor. Good morning. So before we introduce the new approach that we're going to be taking, let's spend a few moments talking about the legacy design, what works, what doesn't work, why we have to redesign it, and how the new redesign is going to address the shortcomings of the existing system. Before we can address the design, I'll have to introduce a couple of concepts about the mainframe. So the mainframe is a monolith. What do we mean by a monolith? That means that there's a single system that contains everything. It contains the SDLC, it contains security, it contains monitoring, storage, database, etc., application server. So we're going to have to be breaking that apart in order to move to a new platform. So this is the InvestOne system, as you can see over here. That's the green box in the middle. The section on the right are the various systems that we interact with from a vendor perspective. This is not going to be a full picture. It would be impossible to fit it onto one slide. But over here, you're going to see the interactions that we have on the right side. On the top are the interactions that we have for data streaming down. So think of this as data coming in. This is transaction data. This is going to be reference data. This is going to be various other pieces of data. Note the two red boxes on the top, one of which is for real time and one of which is for batch, or SFX and EMS/MQ. More on that in a moment. On the left side, we have the interactions that are happening real time. You could think about that as the client interactions. You could think of that as operations who are making changes, things of that nature. Some of them are provided by the vendor. Some of them have been written by us over the years. And finally, on the bottom, we have downstreams. So data comes out in batch, data comes out in real time. And again, you see the two red boxes over here. You have MQ and you have SFX. Let's talk a little bit about MQ and SFX because it's going to be relevant to the whole redesign. MQ is a vendor platform for real-time messaging called message queuing. It's provided by vendor IBM. Pretty standard for decoupling or making messages asynchronous between systems. SFX is a Goldman homegrown solution called Secure File Exchange or Secure File Transfer, which is a wrapper around SFTP. It provides workflow, it provides a lifecycle, auditability, retry, controls, etc. It's important to note that almost all the interactions that happen with the InvestOne system are happening either through SFX or through MQ. There are many systems, there are many approaches that they take, but all of them are either batch or real time, and more about that in a moment. So the box in the middle is the InvestOne ecosystem. You can see that there are 4 boxes. Inside, you have real-time, batch, manual, and data extraction. And those correspond to the 4 types of interactions that we have. On the upper left, you have cash and trading. Those are typically real-time. As mentioned before, those are happening through MQ. You have, on the upper right, various reference data systems. So in order to build a portfolio or a position, it's not enough to have a set of transactions or a set of trades. You have to have information about those. You have to have information about the accounts, information about the products, information about the prices, so to know what the value of a position is. various other pieces of reference data as well. You have the manual entry, that's the human that always has to be in place for when things go wrong, for overrides, for changes that have to happen for when bad data comes in and mistakes happen. And finally, we have the extraction at the bottom, mostly batch, but there is some real-time as well. So various clients or downstream systems from us, you think controllers, think reporting, sending data to clients, sending data to government or regulators, things of that nature, as well as reconciliation with all the other systems that we have within Goldman Sachs that are relying on the same data to make sure that we have consistency. So looking at the existing mainframe architecture, you could think of it as a layer cake. So on the bottom, you have the operating system. It's not Linux or Windows or most of the operating systems we're familiar with. It's ZOS provided by the mainframe, provided by IBM. On top of that, we have the file storage. So first we have DB2, which is relational data, RDBMS standard data tables that we have that similar to most distributed platforms. What are different in the mainframe are the VSAM and flat files. VSAM files you could think of as an index or one single table with one single data type, which is rapidly searchable using a standard tree format. You have flat files, which consist of pretty much everything else. These last two, the flat files and the VSAM, are mainframe specific. The RDBMS data is, well, the DB2 is the platform of choice for the mainframe, but it's very similar to standard relational data that you're going to see in pretty much any system. On top of these two layers, we have the services layer, which sits between the applications and the operating system. So you have the KICS region, which was mentioned by Victor, which is, you could think of it as an application server, similar to Tomcat or various other app servers that we have, which provide a place for installing applications. We have TSO, which allows for batch processing within the mainframe. We have various interfaces and shells, way of interacting with the operating system. And we have security, authentication, authorization, IAM, RBAC, things of that nature, and various other utilities. Built on top of that are the two pieces of infrastructure that represent the InvestOne application. Part of it is provided by the vendor, that's the core, and part of it is provided by ourselves, built over the last 30 years, which is the ETL or orchestration layer. There's also a scheduler. InvestOne generally is an event-driven system. Event-driven system means that rather than initiating actions or polling, we react to events. An example of an event might be an end of day happened. An overnight cycle has completed. A batch file has come in. A pricing file has been generated. Things of that nature. And we react to those events. So there's an orchestration separate from the orchestration that's built within COBOL, but managed by a vendor called TWS that manage the orchestration or the event-driven nature of the application. And then finally, you have the SDLC. This last one is a little bit an outlier in the sense that typical applications don't have an SDLC built in. However, mainframe does have an SDLC built in because, as mentioned, it's a monolith. It has everything. So what are some non-functional requirements that we have? So in every application, there are some requirements that you have in terms of meeting our deadlines, meeting our SLAs, and then you have some requirements that are necessary to accommodate the needs of the business. So as mentioned by Victor, the primary driver of this project is we have to be able to scale to accommodate growth in the business. The business has been growing at a rate of 30% annually. We anticipate future growth. We hope for future growth. We need to be able to accommodate that. That's the primary success criteria. However, it's very important that we do have resiliency. We can't lose our data. We can't have a tremendous amount of downtime. There's a certain amount of downtime that's acceptable. So let's introduce two concepts, familiar to most of us, RTO and RPO. Recovery time objective is how long are we willing to accommodate or how long are we willing to tolerate or accept the application being down? This doesn't mean any data loss. This means that the application is not accessible. So from the perspective of our business, we're willing to put up with 4 hours, and we believe that would not put us on the front page of the Wall Street Journal. We're acceptable to allow us to have a 4-hour downtime with the application not available. However, that doesn't mean we're willing to lose 4 hours worth of data. We have to be able to bring it back up with a reasonable, close approximation of the current data, where we can know what data we lost. So we're willing to tolerate a 15-minute recovery point objective. And that means that if we lose all of our data and we have to bring it up, and let's say, for example, in another region or another AZ, depending on the resiliency model that we choose, how much data are we willing to tolerate that we're going to have to replay? Now, the reason why we're willing to tolerate even 15 minutes worth of data is because, as mentioned before, we're using a combination of SFX and MQ. Both of those are solutions that we can replay the data if necessary. So, for example, in SFX, the data is not deleted on the source server or on the intermediate server, I should say, that operates the workflow between the client and the server. For a certain amount of time, we can replay it if necessary. The same is true of MQ. So while it's drained from the queue, the underlying storage mechanism, the resiliency model of MQ, allows us to replay it as needed. Then there are a couple that are very specific to us and are very specific to our application. Interesting one over here is that recovery to the secondary region, or to whatever we choose as the secondary piece of infrastructure, whether it be region, whether it be AZ, cannot rely on CI/CD. And the reason for this is because Goldman's internal CI/CD also uses AWS, but it uses only region 1. So if we're going to say that our recovery model is dependent on CI/CD, so for example, we switch over to a set of infrastructure, again, everything we do is using IAC and is using CI/CD for the deployment. But if we're going to say that our recovery uses CI/CD, essentially we are limiting ourselves to one single AZ, and it's impossible for us to get that RTO and RPO that we require. So up until now, we've been talking about the mainframe. We've been talking about the existing design. Let's take a few moments to talk about the reinvented design. So the heart of the reinvented approach that we're going to be taking is going to be an emulator. This emulator is going to be provided by a vendor called NTT Data. It's important to note that the emulator is not providing a replacement for the entire mainframe. What the emulator is providing is a COBOL runtime environment. So most of us have not used COBOL, or many of us have not used COBOL. It's another programming language. It has its own compiler. It has its own runtime. It has its own sets of utilities. But it does not provide everything that's necessary to run the mainframe application. Some examples. It doesn't provide us with an SDLC. So yes, it provides a compile environment. You can compile and produce binaries and things of that nature that are used for the runtime, but it doesn't provide us with everything. So the various approaches that we could have taken are outlined over here. I don't want to go through all of them, but these are just all the approaches that can be taken. Some of them involve shifting our data. Some of them involve shifting our application. Some of them involve redesign. The one we decided to go with is replatforming. So what do we mean by replatforming? What we mean is that we're not changing the application logic. Rather, we're not even changing the application binaries. Rather, what we're doing is we're changing what the infrastructure that it runs on, but it should be the identical application. Now, that's not possible to do 100% perfectly, because certain utilities are native to the mainframe, are specific to the mainframe. But in general, we're looking not to redo the architecture, or not to redo the application logic itself. All the code should stay the same. It should just be running in a new environment. We're going to be swapping out some functionality that's provided by the mainframe, replacing that with functionality that's going to be provided by a Linux OS. So if you look at this slide, on the left side we have what's the previous condensed version of a slide from several slides ago. You have the various functionality that's included within the mainframe. You have InvestOne Core, you have the InvestOne ETL, you have that scheduler for event-driven paradigm, you have the SDLC. If you look on the right side, you'll see almost every piece of functionality is there as well. There are a couple of exceptions. However, the box in the middle is going to be the core of the InvestOne application now. So what's there? So we have the InvestOne Core, which is the vendor application. We have the InvestOne ETL, or orchestrator, which is the code that Goldman has provided. We also have the vSAM files and flat files, because those are the mainframe-specific files that are not supported within the Linux operating system. However, what we don't have is, we don't have the database there anymore. We don't have monitoring or various other utilities and security over here anymore. We don't have the database files anymore on the same operating system, because those are going to be extracted into an RDS. We don't have the scheduler there anymore. That's going to be pulled out with a different vendor application. And we don't have various other utilities that are built into the mainframe itself. So this is the architecture without taking into consideration resiliency. We'll discuss resiliency on the next slide, but let's focus on the architecture itself. Starting at the top, we have the VPC, which is, in our case, it's actually a shared VPC. We use a shared VPC model within Goldman Sachs based on The runtime environment or the infrastructure design that we use is called Fast Track, which was developed by Ragini and her team, who's actually here today. Thanks, Ragini. So we have the InvestOne application is going to be running within that shared VPC for our our sub-BU or our division. Within the VPC, we're going to have two security groups. We're going to have two subnets. The first one is going to be the GS routable subnet, and the second one is going to be the cloud routable subnet. Why do we do this? To protect client data. So the cloud routable subnet, which is where our actual application runs and our data gets processed, does not have access to the internet. It doesn't even have access to the GS network directly. Certainly the GS network does not have access to it directly. Instead, we have a GS routable subnet, which has the routing tables, et cetera, and access to both GS as well as to the cloud routable subnet. There are going to be a couple of pieces of infrastructure that are going to be deployed within the GS routable subnet, which will allow for communication bidirectionally with the cloud routable subnet. So what gets deployed within the cloud routable subnet are going to be the core of the application. So as mentioned before, the primary is going to be the emulator. That's going to be the COBOL runtime. We also swapped out the scheduler. So let's look at each of those auto-scaling groups independently. So we'll take the emulator or the mainframe emulator. So we have this auto-scaling group consists of three components. We have the AMI, we have the EC2 instance, and we have the EBS volume. The reason why we chose EBS in general throughout this application, we experimented with various approaches. We experimented with EFS, we experimented with FSX. We found that the best balance of performance and reliability was EBS for our case. We're going to have to make some changes, though, in terms of RDS. We'll get to that. DRS, which we'll get to in the next slide. So the AMI that's provided, this is built internally by Goldman. It includes all the binaries that are provided by the vendor. It includes the binaries that are provided by us. It includes the various utilities that we need. It also includes various components that are provided by technology risk within Goldman for us to be able to safely run this with client data. There's the EC2 instance, which is very important to us. This is the heart of how we get our scalability. We can have various environments, some of which are larger and some of which are smaller. We can spin them up, we can scale them up, scale them down. Since they can all use the same AMI and they all use the same EBS volumes or similar EBS volumes, we can use, let's say, GP3 in one and IO2 in another. That's fine. But from the perspective of the AMI, from the perspective of the AS group, it looks exactly the same. And we'll talk about a little bit how we came up with that later. Almost identical is the scheduler. Again, same three components. You have the AMI, you have the EC2 instance, and then you have the EBS volume for persistent storage. It's important to note that the EBS is critical within this application because, as I mentioned before, there are three types of storage. One of them is going to be the database, relational database. That's going to be pulled down to Oracle, which is the box that we see below the scheduler. But the other two, which are the vSAM files and the flat files, those are all going to be within the EBS. So you could think of us as really developing a database. So that, in the sense that the storage has to be local and has to be fast. The other thing that's deployed within the cloud routable subnet is going to be various Lambda functions. Those are going to be necessary for transferring data in and transferring data out. Within the GS routable subnet, we have a couple of components. One of them is an SFX access point. As mentioned before, SFX is what we use for transferring bulk data across environments. So rather than giving access, within Goldman, we do not give access to S3 buckets to any other account, even other accounts within Goldman. We certainly don't give to accounts external to Goldman. But we don't give access to buckets directly. Instead, the bucket stays within this particular account, and no one has access to it except for our access point. The access point, we grant access using the internally developed RBAC system to other accounts as necessary with the condition that they have to be Goldman accounts. So in this case, we're going to give access to the SFX system to operate on our behalf to transfer data in and out. And we're going to also be installing a network load balancer. The network load balancer acts as a proxy or as a gateway to transfer data from the GS network, inbound traffic into the cloud routable subnet. You notice on the left is a GS proxy. That's for both inbound and for outbound. One of the conditions that the proxy imposes upon us is that it requires MTLS using Goldman client certificates. More on that a bit later. And then things that are not deployed within the subnet but are nonetheless necessary for operating the in and out and back and forth is going to be the SNS for notifications. We have S3 for transient data. We don't store permanent data on S3. All permanent data is going to be stored either on EBS or on RDS. And we use CloudWatch for monitoring. We have EventBridge for, again, this is an event-driven system, so we use EventBridge for reacting to events and triggering lambdas and triggering the various flows based on the data as it gets transferred. And we have SSM. SSM is going to be quite important. More on that in a moment. So this slide is a repetition of the previous slide, but showing both regions. So we decided to do resiliency by region, not by AZ. The reason for that is because periodically a region or access to a region could come down, and it can be down for more than 4 hours. As mentioned before, our RTO and RPO are, we have 4 hours and 15 minutes. We can't tolerate the possibility of it being down for more than 4 hours. So every bit of infrastructure is going to be deployed to both regions. We're going to be deploying the RDS database. We're going to be deploying every aspect, EBS volumes, EC2 instances, the various SSM, S3, everything is going to be deployed to both regions. The way that we're going to be doing our resiliency, if we have to fail over to the second instance, is going to be dependent on the persistent data type. So for the case of EBS volumes, and again, this is for VSAM files, which I mentioned before. These are indexes, or for flat files, or for temporary files and things of that nature. That's going to be using DRS. So DRS stands for Disaster Recovery Service. The approach, this is an Amazon service which acts as an orchestration layer for managing the bringing up of a set of infrastructure on the second environment that should the first environment go down. And the way it does it is by shadowing the environment, the primary environment, keeping it up in waiting in the wings for us to bring up the secondary environment, and then bringing it up by taking snapshots of the volume of the EBS volumes in the primary, and then rehydrating the EBS volumes on the secondary. For DRS, we're going to be using Oracle Enterprise directly. So Oracle manages all that. For cases where for a cheaper environment where let's say for example, in our UAT environment where we only have one region, we don't have a secondary region because we only have one UAT which has both the primary and the secondary, we're just going to be using the standard Oracle, which is a much cheaper license. Finally, for connectivity, we're going to be using an internal Goldman developed DNS solution called Nimbus, which initially points to the GS proxy in the primary region, and in the secondary region, it's configured, but it has a weighting of 0. So Nimbus, which is the DNS solution that Goldman uses, we're not using Route 53 for this because it's within the Goldman network, or at least the connectivity from the Goldman network to the AWS network. So it allows us to give weights based on, as many things do, based on some criteria. So initially, we give 100% weight to the primary region. In the case of a BCP, we give 0% weight to the primary region, 100% to the secondary region. So now let's focus for a moment on some design patterns that we've discovered. These are things that we found over the course of the project that allowed us to simplify and to standardize how we do various interactions with the upstream system, downstream systems, et cetera. And they allowed us to make use of these in common ways to allow us to build other things, as we'll discuss. So the first one is inbound file transfer. So as I mentioned before, SFX is the tool of choice within Goldman for transferring files across boundaries. This can be used for transfer files between AWS and GS. It can be used for transferring files between GS and clients, from clients to GS, et cetera. So when we were looking to standardize this, the approach that we're taking is, to start with, we're going to have a system called MDS. MDS stands for Market Data Services. This is a pricing service which provides market prices for us to price a given asset. Again, we have a position over here that we're looking to produce. A position consists of a set of trades. We don't know the value of the position unless we know the current value of the asset that was traded. So if you bought the asset a month ago, a year ago, we don't know the value of it unless we have the prices. So we need those prices constantly. We get constantly getting feeds from MDS, which is going to various vendors across the street to get prices for various products that we're looking at. So to start with, MDS is going to publish using the same way that it's been doing up until now. We're trying to avoid any breaking changes to any of our clients. So MDS is going to be FTPing exactly as it's been doing for the last 20 years to SFX. SFX, rather than sending us a signal and then us consuming the file directly, instead we're going to change to a push model. And that push model is, it's going to write to the bucket that was mentioned before, again, controlled via the access point so that nobody else has access to it. It's going to be writing to that bucket, and then we're going to be using Event Bridge to listen to those events. When that event gets triggered, we fire a Lambda, which goes to the parameter store, gets information related to this event, related to this file, and decides which SSM automation to kick off. So I think this is a good point to introduce SSM for those of us who aren't familiar with it. SSM consists of a bunch of components, one of which is automations, one of which is sessions, one of which is commands, and one of which is parameters. Real quickly, sessions allows us to create kind of like putty an interaction with a running EC2 instance or something else. Automations allow us to create a workflow. This is very similar to step functions or various other automation tools that are out there. It allows us to do it in a controlled way, repeatable way, handle errors and things of that nature. And parameters allows us to look up information like a directory service, JNDI, or any other place for looking up information in the cloud. The final subsystem is called commands. You could think of this as a SSH into a box. It can be it could be a Windows box, it could be any other machine. In our case, we're running everything on Linux. This allows us to create pre-canned commands that can execute by logging into a box and executing those shell scripts. It could be PowerShell for Windows. We're using Linux. So we kick off this SSM automation manager. And the first thing it does is it logs everything to CloudWatch. This is very important for us to maintain an audit trail, to know when things are happening, to be able to respond when things are not happening, and to keep track of every event as it happens. The next thing it does is it creates a command that logs into the emulator, which is now the mainframe emulator, which is the core application of InvestOne. So it logs in, it goes to the S3 bucket, pulls down the file, puts it onto the EBS volume. At this point, the file is available within InvestOne. However, InvestOne doesn't know about it. Again, as I mentioned before, this is an event-driven system. Until the event gets fired, InvestOne is not aware that it has prices to operate on. So for example, let's say we're waiting to do our end-of-day position generation job. We don't know that the price came in until an event happens. So it fires an event to the scheduler. The scheduler now knows that the price is available. And finally, it goes back to CloudWatch and logs it, saying that this job has completed, or at least the event has been fired. Internally, something might happen, but as far as the data transfer job, we're done. If you look at the bottom, you'll see that there's an SNS path. If anything goes wrong, an SNS topic is notified. That SNS topic sends all notifications to PagerDuty, which is what Goldman uses to manage its on-call, to manage its handling of errors by support. So what are the advantages this system gives us? There's a couple of advantages. One of them is that it allows us to replay this in a way that if we want to give access to support, we do not have to give access to the resources directly to our support team. So our support team occasionally has to do things. Things go wrong like they do with every other system. We would rather be able to wrap the entire job that they're doing into an executable runbook, which can then assume a role which has permission, for example, to execute a script on the emulator, rather than giving access to our support team to be able to execute scripts on the emulator directly. We don't want to do that. So instead, we have a role which is designed to execute, let's say, for example, taking that case, execute that script on the emulator. The support team only has the right to execute the SSM document or the SSM automation. And then the SSM automation itself assumes that role and can log into the machine. This gives us a layer of protection to make sure that our support doesn't inadvertently mess things up. It also allows us to, since we have these executable runbooks, it allows us to test everything in a non-prod environment in a safe way. It also allows us to make things repeatable, and it guarantees that when things happen, they are actually logged. Every single thing is logged because the SSM itself logs everything. The outbound file transfer is almost identical to the inbound file transfer. I'm going to go through it a bit quicker. There's a couple of interesting things that happen over here. Again, in this case, the trigger, or what's initiating it, is coming from within the emulator itself. It's not coming from an external event. In this case, the event is being triggered by InvestOne. It writes the CloudWatch logs like everything else. Step 3 is the interesting one. As I mentioned before, Goldman requires that any communication happening from AWS into Goldman's network, or GSINet as we call it, is using MTLS. However, out of the box, MTLS using Goldman certificates is not available for a Lambda function, which is what we're using. So the way we do this, the way we accomplish this, is by having a sidecar or a wrapper around the Lambda function, which controls the communication to GSINet. That sidecar process does have the client certificate for allowing MTLS with the GS certificate via the GS proxy and over to SFX. So by encapsulating, and again, the failure condition is all there, and finally the CloudWatch is all there. By encapsulating this, again, we can make sure that we can make this repeatable, we can make sure that support can execute it as necessary, and we can make sure that if something happens, it gets notified to the on-call via PagerDuty. Third one is almost identical to the previous two, but is even simpler than the previous two. And this one is for inbound signals. So most interactions happen as batches. We are receiving data, we're sending data, we're consuming data, we're processing data. Occasionally, a batch will happen. An example of that would be, suppose we want it to be known that an end of day has occurred. So Goldman operates by business day, by trading day, for each of its regions. So for example, we want to know, some upstream system wants to let InvestOne know, hey, you can do your processing, no more trades will be coming, it's an end of day. That's a signal. There's no batch file. There's no file of transactions that's taking place. The transactions may have been happening throughout the day. Instead, we want to send a signal. This is relatively simple. We could have done it, you just throw up a Lambda to do whatever it is that you need to do. Instead, we chose to do the exact same process. Again, it comes, I picked MDS because it's an easy one, we've been using it. It sends the same CloudWatch log. It hits the API endpoint, which we could have just exposed directly. And then finally, it logs the CloudWatch. The reason we did this is, again, it gives us that repeatability. It also allows us to control access to the endpoint that our on-call support cannot hit it directly. They have to go through the SSM, which again provides us with controls and logging. So as mentioned before, the SDLC is built within the mainframe. So SDLC we're all familiar with, software development lifecycle. This allows for change management. It's called CI/CD, DevOps, various names. But the heart of an SDLC is the ability to change software to react to new requirements, to react to changes in the environment. So the emulator is not providing us with all the functionality that the mainframe provided. And one of the things it's not providing us is an SDLC. We needed to come up with our own SDLC, but we didn't have an enormous team. We wanted to use off-the-shelf components to make an SDLC which will work, which will be compliant, and is going to be delivering the functionality that we want as quickly as possible. So let's just look at what we're trying to accomplish with the SDLC. So there are certain standard things. It's got to be auditable. If it's not auditable, we're a regulated entity. Our industry regulators will not be happy if we can't prove why certain things happen, what software is running, who made those changes, why those changes happened. It has to be auditable. That's a given. It has to be repeatable in the sense that if we need to bring up the environment, we need to be able to go back to how software looked at a point in time to understand why something happened, because we're dealing with clients' money. And then finally, it's got to be usable by the COBOL developers who are not comfortable or familiar necessarily with the way we do an SDLC in the distributed world. So in order to build out our own SDLC, we tried taking advantage of the tooling that's available within Goldman, as well as various open source and other tools that are available across the industry. I'm going to introduce a couple of concepts over here, a couple of technologies. Many of them will be familiar to you. Some of them may be a little bit new. So the first one is Nix, which is a packaging manager for Unix, for Windows, and various other operating systems. The advantage this gives us is it allows us to pre-package things in a way that each of our developers can have them in a standard format. The next one is Coder, which allows us to very quickly spin up developer workspaces. So we have a team within Goldman which provides these workspaces. You can use them for remote development internally. You can use them for creating prod-like environments. So what we've done is we've used dot files, which is a feature of the coder development, to create install scripts which will spin up your entire developer workspace in a way that consists of all the Nix packages that you need, as well as the IDE that you need, as well as the utilities that you need in order to do our development. So let's go through that. And then finally, we have VS Code and GitLab. The reason why we chose VS Code, even though most of us typically use IntelliJ, is because the plugin that VS Code has for COBOL development is pretty cool. It's actually provided by the vendor that provides our compiler. Vendor's name is Microfocus. They are a leader in the COBOL development space, and they provide their plugin that they provide is available for VS Code. VS Code supports remote development. It has pretty good support for things like refactoring and things of that nature. And it also has a web-based IDE for those of us who like it. And then finally, there's GitLab, which is Goldman's standard for how we do our source code storage. So let's go through the three workflows and how we use the various components and how it came together to make a pretty solid SDLC experience for our developers, for our COBOL developers. So the first one is dev. So when you think about dev, what we really want is that people should be able to iterate quickly, get their code or their binaries pushed out into the system really quickly. It does not have to go through GitLab if you don't want to. You can think of it as running locally. However, we can't run locally because we don't have a COBOL environment locally. So what we use is we use that inbound file transfer that was developed before for transferring files. We just built a piece of code that ships it off to SFX. So again, once it's in SFX, we have a full workflow around getting the code available onto the mainframe emulator. So all we've done is, for the dev flow, is create a set of utilities for invoking SFX or transferring a binary file onto SFX. The UAT environment is a little bit more complicated because this one, by regulation, has to be secure, it has to be auditable. So what we've done here is we've done the same step, the same first step, but we just introduced the Git pipeline in between. So rather than having the developer's workspace itself send the file using our inbound file transfer, instead we have a Git pipeline which sends the file over. This way, everything is in Git. We're using the exact same set of utilities, and it looks the same from a developer perspective, with the exception that things are being deployed via Git pipeline. And then finally, it gets deployed to the host using a set of scripts that we've written on the emulator side. The production side is somewhere in between. So there's a new concept over here introduced called Area, which is an internal storage mechanism that we have within Goldman, which is required to every binary that ends up on a machine somewhere that's going to running production code has to be stored in Area for auditability and repeatability purposes. So what we do over here is, rather than kicking it off the pipeline via your code change, instead we kick it off via either a branch or a tag or a release tag. It's done within the GitLab ecosystem. Add an additional step just for this particular pipeline to send it to Area, and then the rest of it is exactly the same. Except that since it's going to production host, it's limited to which account can execute this. What this allows us to do is, from the developer perspective, they can execute the same set of scripts. The only difference is they have to say which environment it is, and we either introduce a storage to Area, or we introduce a Git pipeline, or we push it directly to the host. And the final step is exactly the same in all three as well. So, as mentioned before, we have a bunch of environments that we need to run. There's lots of reasons for that. If you think about the way InvestOne operates, so it maintains history for the last 33 years. Now, there are certain use cases which require us to have all that history. An example of that is if we do a transaction, we need to know the tax implications. We can't know the tax implications without knowing every single transaction that's taken place within this account for this particular name, because there could be wash sales, there could be various other things that have implications for the ramifications of the tax lots. In order for us to be able to test various systems, we need to be able to bring up upstream systems, downstream systems, we need to be able to bring up a UAT environment, which is going to mirror the production environment. However, we don't want it to be as costly as the production environment. Running a full-scale production environment can be quite costly. We have very high IOPS. We have for EBS, for RDS. We have a pretty expensive machine running the EC2 emulator. The scheduler is not so expensive, just simply the nature of the workload. But what we're looking to do is spin up many environments pretty quickly. So I'm going to go through how we accomplish that. If you look at this, this is an AppDO that I took a couple weeks ago. And on the left side, you'll see the environments. We currently have 10 UAT environments. You can see that 3 of them dominate the cost. Something like 85% of the cost is coming from those 3 environments. Something like 10% of the cost is coming from the other 7. The large environments can be 20 times the cost of the small environments. On the right side, you'll see for all 10 environments together, what are the costs per AWS service? You could see, again, the cost is dominated by 3 services. You have RDS, EBS, and EC2, which kind of makes sense. RDS is our Oracle database, quite expensive. EBS, since we're using high-performance EBS storage, quite expensive. And our EC2, we're using many cores, lots of RAM, et cetera. Again, this is a scalability story, quite expensive. So how do we manage all that? Really pretty simple. We tokenized our code. We're using CDK for all of our builds, using Fast Track, as mentioned. And we tokenized everything in one file. So one file has the differences between all the environments. So one of these is, I think, UAT1. One of them, I think, is UAT4, if I remember correctly. And the difference between them, if you look at, I think it's line 24, you'll see that on the left side, it has 64,000 IAPS for the RDS, for RDS IAPS, and on the right side, it has 3,000. So you can understand really quickly why this one is costing 20 times as much as this one, even though they could be the same size. So this allows us to easily spin up environments which look the same, but are dramatically different in terms of their cost. The final slide that we're going to be discussing today is how do we actually transfer data across accounts? So it's very concerning to our internal tech risk, especially because this includes clients' transaction data, history, current positions, et cetera. So how do we do that in a controlled way? So the approach we came up with it is we broke everything up into 3. So there's going to be 3 keys, there's going to be 3 snapshots, and there's going to be 3 steps in the process. And I'll go through them, and hopefully we'll understand how this helps keep client data secure. So to start with, the production environment, so the 2 environments we're going to be talking about are production and UAT. The production environment has its own key, which is never shared. That key is used to manage its EBS volume. Again, same thing as for RDS. I'm just going to focus on EBS, but exactly the same thing would be for RDS. So, and because those are the only 2 persistent storages that we have, RDS, EBS. So for EBS, we have a private key which is only used by the production environment. Again, there's another private key which is only used by the UAT environment. Neither of those keys can be shared with any other account, and the only thing that has access to actually execute the EBS itself, or to actually open and write to the EBS, is that particular key. We have a process which runs nightly, which will take a snapshot of the EBS volume, step number 1. It will then copy that snapshot using a second key, which is shared with the UAT account. So that second key, or the middle key, is shared between the production account and the non-prod account. There are a couple of interesting things about that second key. Number 1, it can only be shared with another account that belongs to the same application. Number 2, that sharing is not done by us. We don't even have the ability to do that. It's only shared via IAC. This is a control we have in place to make sure that that key cannot just like wander out in the wild. Through IAC, it can only be done to another Goldman account belonging to the same application. So that second snapshot is created during the nightly maintenance stub, again using SSM, and then we're done. So at this point, we have a second snapshot. However, the snapshot itself is not shared with the other account. Instead, we have the second step, which is the share step. The share step has to be run by a human being by assuming an elevated role as a one-off, which is logged and monitored. And that, all it does is it adds the second account as an owner to the EBS snapshot. So at this point now, the nightly maintenance job has copied the first created the first snapshot using the primary key, created the second snapshot as a copy of the first snapshot using the shared key, but has not shared the snapshot. We then have a job, which it's not a job, it's actually done by an operations person, which can, assuming the permission to allow them to share that snapshot with the second account, but it doesn't yet import it into the second account. We then have to go, from the perspective of the second account, we have to bring in that second snapshot, but not just bring it in, but then copy it over, because that key that it's encrypted with is not available for general use by the second account. Instead, we have to copy it over again, copy that snapshot into another snapshot, which is encrypted using the key belonging to the UAT account, and then it can be used to be converted into a volume. I'm going to hand it over to Victor to discuss various lessons learned. If anyone has any questions, they can feel free to come to us afterwards. I don't think we're going to have a Q&A session, but Victor and I will be available if anybody has any questions or comments.
Sure, thank you. So I would say, just to hone on a few things that we learned throughout this process. First is that just getting it running on emulator is the first step. As you just explained, there's a whole book of work to recreate the environment, and everything goes about doing that. The second thing we also learned was we had many consumers and producers of data with our mainframe, and one tenet that we lean towards is not changing the existing interface. Right? We wanted to reduce the blast radius of the number of changes that were happening. So keeping consistent interfaces that we have today, working in the new environment. And then the last one was just a very pragmatic approach. That when you look at a mainframe, you're trying to modernize it, it could be very daunting and overwhelming. But with this approach, we mixed a pragmatic approach just to get it running, lift and shift it, and we've seen that that's been a very successful pattern for us. So some special thanks I must call out here. So Braha Cohen, who's in the audience here, our manager, she's been a great sponsor for us to get this thing going, recently promoted partner at Goldman Sachs.
And I want to give a little, I don't have my mic on.
Okay.
I just want to give a little thanks to Sherry Moran, not a little thanks, a big thanks actually, to Sherry Moran for everything she's done. Not just for helping us with access to resources and things of that nature, but when she didn't have the answer, she was able to hook us up with people from the AWS space who have been really, really helpful, getting us access to the team that was necessary in order to do some of these things. Some of these things were pushing the envelope from the Goldman side, and we just didn't even have the expertise. So she was very, very helpful in the success of the project.
Great. And then, like Gitz mentioned, we'll be around here. Happy to answer any questions or share our experience with anybody here. But thank you again for coming here. It's a really great time. Thank you.
Thank you.